So it's a great pleasure to welcome Jon Aurnou to give our talk today. So Jon got his PhD at Johns Hopkins University, and then he moved to the Carnegie Institution for Science as a postdoctoral fellow. And he's been at UCLA for very nearly 20 years now. So Jon has been doing theoretical and experimental work on rotating fluids with the aim of explaining flows in planetary cores. So he runs the Simulated Planetary Interiors Laboratory, or SPIN Lab, at UCLA. And today, Jon's going to tell us about dynamo generating flows in planetary cores. So over to you, Jon.
Okay, thank you so much. Pleasure to be here. Okay, so thanks. I'm going to be talking today about kind of flows we have in planetary cores. And as I finished it, I add a little clause to the title, Rise of the Rossby Numbers. I'm going to talk a lot today about Rossby numbers. So I've kind of thrown them in there as well. Just an acknowledgement to all the people who have helped on the work presented today, and also in making figures that I'm presenting, but they are not mine. And so, because I probably have too many slides, I will keep going, but I want to be clear all the great work that has gone into this. So I am going to focus today for the most part on the dynamo field we know best, and that would be Earth's magnetic field. And so let's just hop right into Earth's interior. Earth has a radius of about 6,400 kilometers. The outer, about half of the planet, is rocky, it's silicate mantle. And within that is the inner half of the planet is a metallic core. And the radius of the core is just under 3,500 kilometers. And so it's roughly about the size of Mars. So we've got this kind of planet inside our planet. Most of the core is molten. And so it's largely molten iron, but the inner third is solidified. So there's a solid inner core at the center of the planet. Its radius is about 1,200 kilometers. So it's about 2/3 the size of the moon. So we've really got this kind of nested set of shells, and it's a rather amazing structure. Okay. Let's talk about what's happening in the core. In the outer core, in this fluid region, we have a dynamo. And in that dynamo, what's happening is the kinetic energy of fluid motion is being converted into magnetic field energy. There's no permanent magnetism related to the dynamo. It's simply too hot, amongst other things. So it is not that we have a permanent magnet. We've had it for a long time. There's geologic evidence going back about 3.5 billion years, showing that we have a long-lived paleo field, maybe even older, but that's where people really start arguing rather vociferously. The field on average is aligned with the rotation axis of the planet. It undergoes these interesting polarity reversals where it can flip direction. And lastly, I should mention that it's very well coupled to the mantle. And really that means the mantle throttles the core, right? This is essentially, the dynamo is essentially a heat engine. However, it's a heat engine inside a big mantle blanket. So the mantle controls how much heat fluxes out of the core. And that really sets the energy budget for all the processes occurring in the core. Okay. One thing I should mention, though, I'm talking about energy being controlled by the mantle, but currents are not large in the mantle. J is essentially 0 in the mantle. It's not a good electrical conductor. So since J is 0, we can consider the field outside of the core mantle boundary to be that of a potential. So we have a potential field solution out there. And so we can write that down. Classic, we've got spherical harmonics in theta and phi. We've got we have data at the surface of the Earth, as I'll show this in the next slide too, out to a maximum spherical harmonic degree 13. And that's actually shown here in this nice image from Chris Finlay. In addition, we have a radial fall-off term, and we measure in time the strength of each of these harmonics via what are called Gauss coefficients. And so this is an image of the radial component of the magnetic field at right here shown at about 1600. And you can see most of the field's coming in the north and, or sorry, going out in the south and coming in the north. So it's largely an axial dipole, but there are other components in there as well. And if we play this movie, we can see the field varying in time. And so this is the historical field over about the past 400 years. Again, movies made by Chris Finlay, and actually he stitched together 3 different models in making this movie. And that's the field over the past 400 years at the surface. And it's dominated at the surface largely by the axial dipole component. But there's a lot of other data in there. As this shows, we have information here out to Lmax of 13. So we can then, because it's a potential field, propagate that solution. We can move this in from the surface of the Earth to essentially the core mantle boundary. And then we see the higher harmonics are much stronger at the surface of the core. And you see a lot of really interesting structures and a lot of interesting dynamics. So this is a dynamic complex system. Okay, why can't we see beyond Lmax of 13? Well, so here's a nice plot from Hao Cao showing a bunch of different fields of a number of different bodies. The moon is shown here with the black points at the bottom. That's the lunar crustal field. Mars is crust, so this is permanent magnetism. This is the magnetism locked into the crustal rocks. The Mars crustal field is shown here in blue, and Earth crustal field is shown in red. However, and these all fit nice theoretical curves shown in the background for a randomly magnetized spherical shell. However, you can see on the left-hand side, Earth's field cranks up as we go to low degree, and that's from the core dynamo field. And what you see is that those 2 solutions intersect. Earth's crustal field intersects the core field at about 13 for a spherical harmonic degree. And so we really can't see the core field to higher degree. It's really blocked, and it's blocked by the crust. And so we're stuck in with this relatively low spatial resolution view of core processes with a maximum resolution corresponding to structures about 1,700 kilometers in scale on the core mantle boundary, so fairly large. And then if we make estimates of flow, they could be a radically different set of ranges. They may not tie that well to Lmax of 13, and that raises, really for me, the point that we need to have our dynamics accurately laid out. This is a very remote system. All these planetary dynamos are. Earth is no different, very remote. And some of the big questions amongst many are, what flows actually generate the magnetic field in Earth's core? What are the velocities? What are the flow and magnetic field structures that are actually dominant in the core? And what are their scales? Okay, so let's get to it. What drives core flow? First off, thermocompositional convection. And so here's a close-up of Earth's core from John Chang. And the buoyancy source, or what appears to be the dominant buoyancy source in the core, is that the inner core, the solid inner core, is actually growing over time. As the planet cools, the inner core is growing outwards. And as it does so, it releases latent heat and compositional components as well. So there's both thermal and compositional buoyancy being released, the spherical gravity field. And so if I go in the lab and simulate this rather inexpensively in the lab, that then drives convection, yes? So we release buoyancy and we get radial convection attempting to occur. That, though, is skipping the effects both of magnetism and rotation. Okay, So if we include rotation, it becomes a bit different. And so here's a top view on a rotating tank of water, about 18 centimeters deep by 80 centimeters across. And I'm just going to very quickly show the basic idea what happens when we add rotation. I just sprayed on some food coloring. It's slightly denser, same temperature, but slightly denser than the water. And so we get a boundary layer filled with dye that's slightly denser and therefore buoyantly unstable. And in this rotating system, I'm going to get rid of that background. In this rotating system, these get wrapped up into swirling flows. Looking at them a little closer up, there they are. They're the tops of these solutions. They look a lot like Chandrasekhar and George Voronez's solutions because they are. This is really the onset mode. And they also look a lot like what you see at the top of our full spherical shell solutions, image from Thomas Gastine. And looking at this again obliquely from the lab frame, you can see we get these tall helical structures. And so this is the fundamental flow you're going to get in a rapidly rotating system. And we'll be talking about that really for the rest of today. Okay, so that was rotation and convection occurring, but what happens when we include magnetism, right? In dynamos, magnetism should not be skipped over. And so here's a nice solution from Andrei Shako. This is a planetary dynamo model, and the rotation axis is shown here vertically. And we're looking at the radial velocity field. And again, what I hope you can see, this is just a snapshot, is that the flows still remain well aligned with the rotation axis, similar to the lab experiment I showed you before. And this is the case even though the magnetic field arguably is strong. And we won't get into what strong means here today, but arguably this is what's called an Elsasser-1 dynamo, where the Lorentz forces appear to be comparable to Coriolis, and yet the flow field isn't greatly altered from a rotating solution. And so it's still a quasi-geostrophic flow where rotation tends to dominate the fluid dynamics. And I don't have time to really show that, but this has been found over about the past 5 or 6 years, starting with the model of Calkins 2015, and then many people have been finding this for the past in the more advanced models, that at leading order, these dynamo flows are all quasi-geostrophic, so rotationally dominated. Magnetic fields come in at second or higher order. Okay, so we can kind of turn off the magnetic field then in our picture. And we can talk about convection in a rotating core. And that's what I'm going to do for the rest of today. So what I'm going to do is present for the rest of the day a novel framework for trying to assess the flow scales and velocities in a rapidly rotating convection system, in a rapidly rotating core. And this is work carried out recently with myself, Susanna Horn, and Keith Julian. And we've actually tried to not just cover rapidly rotating cases like in planets, but we want to do the full gamut. We want to do slowly rotating and rapidly rotating end member cases. So we don't want to assume we're on an Earth where rotation is incredibly strong. We want to be general. And the linchpins of these arguments, as you're going to see again and again, are 2 different Rossby numbers called the convective Rossby number and the local Rossby number. And we're going to show they're comparable as well. And I want to just say this, for this particular study, I just want to make clear, this really was a strong collaboration. I really just wanted to get out there and try to tie everything together from the slowly rotating to the rapidly rotating regime. Susanna made clear that to do so, to talk broadly across the community, we need to use the convective Rossby number. And then Keith tied it all together at the end by making the theory work. Okay, and so let's get into that. Okay, here are our governing equations. We have Kuznets-Navier-Stokes, so solenoidal flow. We have inertia there on the left, and Coriolis, pressure term, buoyancy term, viscosity, and a Lorentz term. temperature fluctuation equation. Again, we have essentially time derivative and advection for the temperature anomaly, advection of the background gradient, and diffusion. And then we have T bar is the horizontally average temperature field. So that's the mean temperature profile. And then we have the induction equation. Now, I mentioned that we're going to throw out magnetic fields for today and just worry about the rotating dynamics. So there we are, much simpler system. Okay. And in this world, we're going to, I'm going to simplify. We're going to make our spheres into cylinders or plane layers or shells. The scaling arguments I'm going to give hold in all of them. And so let's for now just go to my lab and look at a cylinder. And the characteristic system has a temperature gradient with a temperature difference of delta T over some height h, and a vertical rotation rate omega. Okay. The characteristic scales, which we'll be using in all our estimates, are a length scale L, a velocity capital U, and a temperature anomaly of theta. Okay. All right, so the control parameters in this system are the following. We have the Rayleigh number, which is the effective buoyancy force in the system. The Ekman number, which is effectively the non-dimensional rotation period. The Prandtl number tells you about the material properties. It's the ratio of diffusivities, viscous over thermal. And some of the output parameters are the Nusselt number, which is the total heat transfer over the conductive component. The Reynolds number, which is essentially the momentum transport. And then the Rossby number, which is the ratio essentially of the rotation time scale to some advection time scale. Okay. Now, if we look at these on Earth and in Earth's core, these are rough estimates. The Rayleigh number is somewhere between maybe 10 to the 20 to 10 to the 25, 10 to the 30. That one's actually very hard to estimate. I'll just call it 10 to the 22-ish. Ekman number, we know moderately well. It's about 10 to the minus 15. Prandtl, about 10 to the minus 2. The Nusselt number, and here I'm talking about the superadiabatic Nusselt number, is about 10 to the 5. Reynolds is about 10 to the 9, so the flow is turbulent. And the large scale Rossby number is 10 to the minus 6. So we have what I would argue would be quasi-geostrophic turbulence. Turbulent flow on the large scale is 10 to the 9, but the Rossby number is very slow. So that turbulence is massively impacted by the effects of rotation. Okay. Let's go a little bit deeper into the Rossby number. So we're going to be talking about these a whole bunch of Rossby numbers. One of the ones we'll be focusing on a lot is the local Rossby number. And so that is the ratio of the rotation time scale and the local, basically vortex turnover time, right? So it's the inertia on the active convective scale in a given system. And then the other one we'll talk about a lot is the convective Rossby number. And this is ROC. I just want to make clear, that's not the critical Rossby number, it's the convective Rossby number. There's no critical Rossby number. But there is this nice parameter. I'm just going to go through this because it shows up so many times. It's the square root of G alpha delta T, where alpha is the thermal expansivity, G is gravity, delta T is this temperature difference across our layer, 4 omega squared H. Okay. And so we can rewrite that group as Rayleigh times Ekman squared over Prandtl, whole thing to the 1/2. And that is an estimate of large scale buoyancy over Coriolis, or that's been the claim since the time of Gilman in his 1977 paper, where I think he first derived this. In a very nice paper, it was one of the first studies of solar convection zone physics. I believe he went up to spherical harmonic 16 at the time, and it's actually an amazingly impressive study. And in that, he first defined this parameter, as far as I can tell. And it's really ubiquitous now. So here it is in a couple of different studies used as the control parameter. So the one on the left is Horn-Shishkina 2015, and on the right is Weiss and Allers 2011. Both studies of rotating convection, and both are coming from what I would call the fluid physics community. And in the fluid physics community, the initial focus or the philosophical base is non-rotating convection. It's Rayleigh-Benard convection. And so you start at a given Rayleigh number. Let's look at the image on the left. In Susanna's study, they're fixing the Rayleigh number, the buoyancy, and Prandtl's fixed at 0.8. And then they're increasing along each of these data sets the rotation rate. And in doing so, starting from 0, they start on the left-hand side, and then they increase the rotation rate, and the convective Rossby number is effectively what's being changed. And so it's thought of as the control parameter for all the rotating convection physics. And the same thing in the study to the right by Weiss, where here they're doing the same thing essentially, and they're, I think, changing the aspect ratio of the tank as well. But the essential control parameters, the convective Rossby number, and actually in this study by Weiss, they just call it 1 over Rossby. It is simply, there is only one Rossby. It's the convective Rossby number, okay? In addition, here are some studies by, on the left, John Chang, so geophysics from more of a geophysical aspect, and on the right by Thomas Gastin, where he's simulating essentially cool stars in spherical shells on the right. And in the image on the left, what they're trying to do is now collapse all their data in the study of Chang et al. And in image B, they're trying to collapse it in terms of a local boundary layer Rossby number. Pretty good collapse of all their data. And on the right, they do the same thing with convective Rossby. And again, it collapses the data fairly well. So people are often trying to collapse their rotating convection data with either local Rossby numbers or convective Rossby numbers. And on the right, we see a very nice compilation image from Gastin, where he's plotting the equatorial zonal velocity on the outer boundary in a rotating spherical shell simulations, where he's trying to figure out what controls the direction and speed of the equatorial flow in rotating spherical shells. So essentially in planetary fluid layers. And there is a fundamental change here that I think you can see, and it maps fairly well to a convective Rossby number of order 1. Okay, so again, not the control parameter here, but a very nice collapse parameter. So I just want to get that across. Convective Rossby number is then used throughout all these different studies and all these different investigations of rotating convection. And our goal then is to try to tie all this together and in a way provide a deeper understanding of what convective Rossby means, so that maybe we can understand what it's doing and what it's controlling a bit better. Okay, so to get started then, let's define slow versus rapid rotation. We're going to define the slowly rotating regime to be that in which the fluid inertia swamps the Coriolis term. And we'll define the rapidly rotating regime simply as when the inertia of the flow is much less than the Coriolis term. And so let's scale these. And in both cases, we'll get u squared over L on the left on this convective scale is greater than on the right, the Coriolis term in the slowly rotating regime, and in the rapidly rotating regime, that inertial term will be will be less than. So if we again now just cross multiply, then we get that u over 2 omega L is much greater than 1 in the slowly rotating regime, and it's much less than 1 in the rapidly rotating regime. Okay, well, that is the local Rossby number. So the difference then between a slowly rotating universe and a rapidly rotating universe is defined on the scale of the convection itself, and we can think of it in terms of this local convective scale Rossby number. Okay. Now, let's start looking at the slowly rotating case. In the slowly rotating case, shown here, here's an image of spherical shell convection by Thomas Gastine. That's the temperature field. And on the right is another very slowly rotating case by Jules Abati at UCLA. This is just shadow graph in a tank of oil, and you can see the massive complexity and the large scale overturning flow you get in a very slowly rotating system. And actually, these are so slowly rotating that both of them are actually non-rotating. and we're going to call these similar systems, and they will scale similarly. And so looking at the scaling, we're going to assume a free fall inertial momentum balance where we have buoyancy mapping perfectly into inertia. And so all the potential energy in the buoyancy field is being mapped into flow inertia. And if we then scale that, we get U squared over L is about G alpha theta. I have, some very loud birds right outside my garage. Is that coming through? You guys hear that? That's fabulous. Yeah, it's actually a mating pair of hawks. You never know when they're coming by. They're literally right outside. Okay. And so we're going to assume in the slowly rotating universe that theta scales roughly as delta t, and L is about the system scale. And where am I getting that from? Well, that's been found in many, many non-rotating convection simulations and studies and experiments. And so I'll show you some results here from Vogt 2019, where this is a simulation carried out by Susanna Horn as part of that study. It is looking at a tank of liquid metal, aspect ratio 2, and there's convection in that tank. And what you see is you get a very large scale flow. The green line shows essentially the axis of the largest scale flow, the so-called large scale circulation, the LSC, and orange is perpendicular to that. So if we look within the upper right along the plane of the large scale circulation, you can see that the flow itself is system scale. So a good choice of length is H. And if you look on the right at the midplane temperature field, I don't know if you can see, but the temperature is going from minus 0.5 to 0.5, and that is what's mapped in the color field there. So the temperature anomalies are order 1 in this system. And so in this little, small piece of liquid metal, which is our representative for a piece of planetary core, okay, in a non-rotating world, you can have large scale flows and delta T comparable to the signal across the entire layer. And so if we use those scales, sorry about that, then we can then rewrite the scaling up above. U squared over L is G alpha theta. That then turns into U is proportional to the square root of G alpha delta TH, which is the free fall velocity. The classical free fall velocity pops right out. And we can now use that to define a local Rossby number in our slowly rotating system. So now it's U over 2 omega L. L, though, is H in this world, and U is free fall. And if we put those in, now sub in G alpha delta TH to the 1/2, sub that in over 2 omega H. Okay, then it becomes 4 omega squared. You get an H on the bottom, and we end up at the convective Rossby number. So in the slowly rotating limit, the local Rossby number is synonymous with the convective Rossby number. They scale similarly. Okay, and so in this world, the convection scale Rossby number is the system scale Rossby number. L is H, so ROL is ROH. They're both the same, and they're also co-scaling with the convective Rossby number. Okay, and lastly, I just point out that this ROC definition actually is what's in Gilman 77. So the original definition really does correspond to a slowly rotating framework. And in a sense, that's what everyone's been using since, no matter what the system they're in. Rapidly rotating, slowly rotating, intermediate rotation. Typically, this is the definition chosen. Okay. Now let's go over to a rapidly rotating system. And so now another nice image from Thomas Gastin from his 2016 paper. Now we see we have this well-aligned flow, this columnar flow, as we showed in that original laboratory experiment. Here's another experiment from Jules Abate. And now it's rapidly rotating convection. So same exact system. Prandtl number here is 21. Rayleigh is about 4 × 10⁻11. And you get this very beautiful turbulent yet aligned flow. Okay, so let's start to investigate this flow. In this world, we have to worry about the vorticity of the system because it's rapidly rotating. And so we'll take the curl of Navier-Stokes and look at the vorticity equation. So we have time variations in vorticity, advection, then we have vortex stretching, buoyancy torques, and the viscous term, okay? And we're going to do essentially the classic turbulent CIA vorticity balance, which has been done many times before in this system. We're going to do it as well, but we're going to do it again within our ROC-based framework. And so we're going to claim that if there's diffusion-free turbulence in a rapidly rotating quasi-geostrophic system, then that will essentially be a balance between inertia, Coriolis, and buoyancy torques, okay? And it's called Archimedean because I guess CIA sounds better than CIB. I don't know, but it's always how I've seen it. Okay, so scaling these 3 terms, we then have U squared over local L squared for the inertial term. Coriolis is 2 omega over the larger scale H. So there's a large scale vortex stretching of the background vorticity. And then we have the buoyancy torque, again, on the scale of the convection, so on this scale L. And I want to point out that this is really fundamentally different from the slowly rotating system. In the slowly rotating case, there's really only one, characteristic convection scale. It's H. It's essentially isotropic. It's large scales in both directions. So both, L is comparable to whatever the large scale is in either direction, while in the rapidly rotating system, this is not the case. We still maintain larger scales in the rapidly rotating system along this axial direction, right? Why? Because it's quasi-geostrophic, so the leading order balance is geostrophy, is Coriolis versus pressure. And in contrast, the horizontal scale is very small in that world. So we're going to take L to be the perpendicular scale to the rotation axis. It's smaller. And there then is a very strong anisotropy in these flows. And we're going to take that into account when we're looking at L versus H. In contrast, the velocities are not strongly anisotropic. Here's some recent data from rotating convection in that same tank of liquid metal. Again, paper by Tobias Vogt. And what we see is that this shows ultrasonic Doppler measurements that he made in our liquid gallium. And what you see is that even by 4 times supercritical, the perpendicular component and the vertical component of velocity become order 1. So they're comparable. So we're only going to use 1 scaling velocity. And we do not, in a sense, we don't break that into 2 anisotropic components. It's just the length scales that are anisotropic in this system. Okay, so let's look at inertia versus Coriolis. And when we do so, we have U squared over L squared is about 2 omega U over H. And so we can rewrite that. L over H then becomes U over 2 omega L. Okay, so that's the local Rossby number. So we have a nice relationship for this anisotropic length scaling. And if we then estimate our temperature anomaly in the system, we'll do that by balancing essentially the advection term for the anomalies with the advection of the background temperature gradient. And when we do that, we then get U theta over L goes as U delta T over H. Well, U drops out then, and we get theta over delta T is about L over H. Okay, and we know L over H goes as local Rossby. So we have two very nice relationships here. Theta over delta T and L over H are both proportional to the local convective scale Rossby number, which in this regime are much smaller than 1. Okay. Okay, now let's go to another of our possible balances. Let's balance the Coriolis term with Archimedean. So vortex stretching versus buoyancy torque. And if we scale this, we get U goes as G theta H over 2 omega L. Yes, I'm just rewriting the terms on the left. And we can now multiply top and bottom by delta T and rewrite it as such. G alpha delta T over 2 omega. And then in parentheses, we get theta over delta T and H over L. Well, theta over delta T goes as local Rossby, and H over L goes as 1 over local Rossby. So these terms then effectively are order 1 when multiplied together. And we end up with a classical thermal wind velocity, G alpha delta T over 2 omega. Great. In a sense, nothing is surprising there, but that is what we should get. So the fundamental scaling velocity in our rapidly rotating system is thermal wind. Oh, sorry about that. Oh, horrible. There it is. And so again, here's data from ultrasonic measurements by Vogt, where he's measured UZ, and it's actually his maximum UZ as a function normalized by the thermal wind prediction. And you could see in the range of supercriticalities we could study from onset up to about 20 times supercritical. These are all order 1. So this is indeed what's found in these rotating convection systems, or at least in our liquid metal system. Okay. So now let's check local Rossby again. So local Rossby, now it's going to be whatever our scaling velocity is. In this case, it's thermal wind over 2 omega L. And plugging in, we then have alpha G delta T over 4 omega squared L. And L is, in this anisotropic system, it's ROL times H. So we can sub that in. And then what I think you can see is then we have 1 over L on the right-hand side and ROL on the left-hand side. I'll cross multiply and take the square root. And you see that ROL is then square root of G alpha delta T over 4 omega squared H. That's the convective Rossby number again. So the local scale dynamics, which are defined in a sense by ROL, are once again scaling with ROC. They're again scaling with the convective Rossby number. And that's novel. That's not, and that's, I want to point out, that's not Gilman. Our ROL, as we've defined it on the left-hand side, it's not U free fall over 2 omega H. In the rotating system, in the rapidly rotating limit, that's not right. We should be thinking of the local Rossby number as U thermal wind over 2 omega, some local scale L. And yet we still end up at ROC. Okay, so that's really interesting. In both limits, we end up with the same relationship. And it's wonderful in that this is often used as a control parameter. So this control parameter maybe is used ubiquitously for this reason. It is a very meaningful scaling parameter and defines the local scale dynamics in both the slowly rotating end member case and the rapidly rotating end member case. Okay, why? Why the heck is that? So let's go through why that is actually the case. And I think the easiest way to do that is by looking at timescales, right? And so we can think of ROL as the ratio of tau omega over some advective timescale. So let's define those timescales in both the slowly rotating case and the rapidly rotating case. In the slowly rotating case, it's tau free fall, which is h over the free fall velocity. In the rapidly rotating case, it's L, this column scale, which is this width, which is rather narrow, divided by U thermal wind. And so let's take their ratios. Let's take the ratio of not tau omega. We know tau omega divided by tau omega is 1. Let's take the ratio of our two advective scales. And if we take the ratio of tau free fall over tau thermal wind, then you get a ratio of the lengths. You get h over L, and then in parentheses, you get U thermal wind over U free fall. And now let's plug in for U thermal wind and U free fall, and you get this. One, h over L, we've shown before in the rapidly rotating framework, is 1 over local Rossby, which is 1 over convective Rossby, right? They're the same. So on the left, h over L, I'll turn into 1 over convective Rossby. And now let's look at the velocities inside the parens there. Alpha g delta t over 2 omega. And it's normalized by the free fall velocity, alpha g delta th in a square root. And if we simply rework that, you can see it's 1 over ROC, and then inside the parens turns into square root of g alpha delta t over 4 omega squared h. That's convective Rossby again. So this term's order 1. That's really interesting. So essentially what that means is the slowly rotating scales for velocity and length are much larger than either of the scales in the rapidly rotating system, right? The orange, both U and H in orange are huge relative to U thermal wind and L in the rapidly rotating frame, but their ratios are comparable. Okay, and since their ratios are comparable, you end up with the convective Rossby number being comparable to the local Rossby number in both frameworks. Okay, what else can we see here? Well, now if we take this line above, we see that we have h over L times the ratio of velocities is order 1. And again, h over L is 1 over ROC. So then we can also write that ROC can be thought of as the velocity of the thermal wind to free fall. And that's a very different definition than the original slowly rotating definition from Gilman. And I think this may be a more useful definition. I think I'll come back to that at the end, but I want to keep that in mind. That holds in both systems. That applies both in slowly and rapidly rotating universes, and I think it might be more useful in the end for how we think of ROC. In addition, we can rewrite that and simply point out that U thermal wind is then ROC times free fall. So it's a very nice tie, very clean tie between the scales, between the slowly rotating and the rapidly rotating system. Okay, so then we can tie all our scalings together. On top, we have the rapidly rotating scales, and on the bottom of all these ratios, we have the slowly rotating. They're all proportional to ROC, which is comparable to ROL. So that's very clean. Okay. And in terms of local scaling comparisons, now let's start focusing on the rapidly rotating regime. Local Rossby, okay, fine, I've said that like 1,000 times. It's comparable to ROC. But typically we don't measure ROL, right? Typically we measure the system scale Rossby number. It's very hard to actually get the scale out as well as the velocity. So typically we just measure the velocity and you report a large scale Rossby number, ROH. Okay, so if we take ROH, that would just be the local Rossby number. And then we'll multiply it by L over H, and we'll come up with a large scale Rossby number. And if we're in the rapidly rotating limit, then U thermal wind over 2 omega L, that's the local Rossby number, which is ROC, right? We're saying that those are comparable. That's the line above. And then L over H, that's ROC as well. So then we would get that the system scale Rossby number is proportional to Rossby, convective Rossby squared. Okay. Nice. And playing with that further, then we can say L over H is proportional to the convective Rossby, but using the relation above, that means the length scale ratio should go as the large scale Rossby to the 1/2. And that naturally comes out, and that's been shown actually very nicely in a recent paper by Céline Guervilly. And they go to very low Ekman number in 3D and then 2D simulations. And they do indeed find a Rossby to the 1/2 scaling for the large scale Rossby number when measuring their L values, L over H. So good, so that works. Okay, let's compare our very simple ROC-based universe to what else is out there. If we look in terms of the velocity scalings, what's typically been used in the geophysical community is a system scale heat flux based Rossby number. And that's because typically with planets, we can estimate the heat flux, and stars too. We can estimate the emission from these bodies. Very hard to measure delta T, very hard to actually estimate the Rayleigh number, but we can probably take a shot at Q, at the heat flux coming out. So when you do that, when you do things in terms of a heat flux, then you get what's called Rossby CIA. That's how it's often referred to in the literature. And again, I just want to say CIA here, we're all doing CIA scalings, but this is the flux-based one. And it's Rayleigh times Nusselt, the heat transfer, Ekman cubed over Prandtl squared to the 2/5. Again, this has been found all over the place. I've left out a -1. It's Nusselt -1 if we're going to be precise, but if Nusselt's large, let's just lose the -1. Okay. And now I just want to tie this to what we've done, which is really everything I've shown today is based on the temperature drop delta T, not the heat flux. And so and often it's been claimed that these are two different laws. And I want to make clear they're not. Everything ties together here. It's very clean. So we take a Nusselt number and scale it with our same scaling arguments. Then in the rapidly rotating limit, we'll get U thermal wind times theta. That's the turbulent heat flux, divided by, for Nusselt number, it's divided by what's conducted. So kappa delta T. And then that divided by H, so the H comes to the top. And if I play with that, theta over delta T gives you a Rossby, blah, blah, blah. We then get Rossby times H, which gives us L. Okay, futzing around, you can then rewrite that as U thermal wind times L over kappa. So it's just a local Peclet number, right? Which makes sense. The heat is simply being transferred by the local scale advection. And when we rewrite that with our definitions for L and U thermal wind, that comes out to be Rayleigh to the 3/2, Ekman squared over Prandtl to the 1/2. Okay. Now, if I sub that in for Nusselt up here, I won't do it. I knew this would take too much time. But if we do that, then actually we get everything to work out. All these cancel essentially, and you end up with Rossby squared. So there's no difference. These are all the same arguments. And in a sense, you can say, well, okay, fine, right. So that's a well-known scaling law, but these all tie together. And so I guess I'm not going to go through any of that here today. We've done everything here in terms of a delta T-based universe, You can do everything in terms of heat fluxes, and we can tie all of them back and forth. And the point here is simply that in the delta T based framework, everything's very clear. There is one ROC, it is proportional to ROL, and it gives this nice scaling between the non-rotating and the rapidly rotating worlds. Okay, just briefly looking at transport parameters. In the slowly rotating limit, we have a free-fall Reynolds, free-fall Peclet, and again, free-fall Peclet for the local scale transports. If we transform these to the rapidly rotating system, then they're all modified by ROC squared. We've subbed out UFF for U thermal wind. We've subbed out H for L. Each of those substitutions gives us one factor of ROC. So it's a very simple transformation. In contrast, if we do the system scale, then we're not subbing out H, we're leaving H as is, and we're just exchanging U free fall for U thermal wind. So we get one factor of Rossby. So that's very simple. And that is, in a sense, our point. And so I want to say that really ROC ties the room together, right? That's the idea I want to get across, is that you can really, there's a lot going on in the system, and yet in this framework, ROC is comparable to the local scale Rossby number. And we have these very simple relations between all the different transport phenomena. So ROC really ties things together. Okay, I only have a couple minutes left. Briefly, I just want to get across that this velocity-based definition of ROC, maybe it might actually be a little more useful in the end, in that what it's saying is if ROC is small, then U thermal wind is the smaller velocity. Okay, that's going to be the scaling velocity. If ROC is large, then U free fall is the smaller velocity. That's going to be the characteristic scaling velocity. In a way, you can think of it that simply. It simply defines the dominant velocity in the system. Just briefly looking at experiments, how well do all these work? For slowly rotating systems, if you look at the velocity scale, it's very close to free fall. This is, again, ultrasonic Doppler data from Vogt. And if we go into the rapidly rotating system, we really do get thermal wind. Great. So those both hold up. If we look at delta T's, if we look at theta, in the slowly rotating system, we can show that we get delta T's that are comparable to predicted. I couldn't find anything for the rapidly rotating world. We're now starting to look that way. It'll be interesting to see what we find. It may be, I think Julien Aubert did this at some point. I couldn't find it. And I've never made those measurements. Okay, in terms of length scales, again, in the slowly rotating limit, yep, system scale works. And in the rapidly rotating limit, it is about ROC, which corresponds to system scale Rossby to the 1/2. Okay, experimental comparisons. I thought I'd kind of hold my feet to the fire and see for our two cases that I keep showing, does this work at all? So on the left is Thomas Gastine's beautiful case, and on the right is Jules' really elegant silicone oil experiment. And here's what you get for our simple ROC prediction, no prefactor, just ROC. The yellow line shows the predicted scale. It's pretty fat. And in contrast, here's the onset scale. And it actually looks like onset actually works a little better here, but okay. And if we do the same thing in Thomas' experiment on the left, I would argue ROC and onset scale both work. Okay. So coming full circle and being out of time, let's just do Earth really quickly. Again, the big questions were, what are the scales of these flows? What are they doing in there? And so if we use estimates for ROH, for the large scale Rossby number. For Earth, we get a value of about 10 to the minus 6. This corresponds to flows of about 0.3 millimeters per second, corresponding to about 10 kilometers of motion per year, which we can see in the magnetic field. And so then ROC would be about 10 to the minus 3. So then we predict that the local scale Rossby number in Earth's core is very small. It's order 10 to the minus 3. That's already interesting. In addition, we can then say L is about ROCH. So L is about 10 to the minus 3 times the system scale, which gives us a column diameter of order 2 kilometers. And again, I don't have any prefactors here. It could vary by an order of magnitude either way. But no matter what, that's still incredibly small. So these are very small, very tall, rapidly rotating structures. I would also point out, I've skipped all the MHD here, but we've made an estimate of the crossover scale between quasi-geostrophic and MHD dynamics. And actually, we also get a length scale of about 2 kilometers, slightly fortuitously. So maybe that's not outrageous. That would give you then at 2 kilometers an azimuthal wave number of about 10 to the 4 in the core, and a local Reynolds number of 10 to the 6. So local Rossby is 10 to the minus 3, so it's still rapidly rotating, and yet even on that local scale, it's highly turbulent. The local Rossby number is 10 to the 6. And the local magnetic Reynolds number on that scale would be about 1. And that's interesting too. That suggests that if there are these small scale structures underlying all the dynamics in the core, they probably are not at a massively high RM. That's very unlike, let's say, a solar model, right? They may just be, we could almost treat them as with a quasi-linear approximation, which is interesting. And so you can think of these little inductors, and they're all probably quasi-linear. Okay. In summary, my apologies, I know I'm right out of time. Very nice. We've developed this new framework for both rapidly and slowly rotating convection. Everything's tied together by a convective Rossby number. We've done this with doing, I think, possibly for the first time, a CIA scaling using delta T as the scaling for temperature, not a heat flux. We've shown ROC is proportional to the local Rossby number, which really seems to tie a lot of things together. And we really haven't done any quantitative testing at all, but that will be of interest. Furthermore, we have not, these are really two end member cases, ROC either really small or ROC really large, but almost all the data lies in the ROC1 regime. So there's, we really can't talk about the intermediate regimes where almost all our actual data exists. So there's much more to do there. Okay, thank you very much. And
thank you, John.
Where I will stop. Yep.
Just before we get on to the questions, I've been asked by Kathleen to advertise the George Batchelor 100th event is on the 29th, the 30th and the 31st of March. And if you would like to go, could you please register before the 24th of March? Obviously, it's online, an online event.
From the beautiful comparison between I'm looking at the wrong camera, the beautiful comparison between the experiment and the simulation image, with the EC and the ROC, you presented all this good argument for why we should believe in the ROC scale. But it really, in the experiment, it really is a bit more like the onset scale. Do you have any, does it need to have some coarsening process? Do you have any kind of argument about why?
So in a sense, yeah, very nice question. So let's go back to here. Can you guys see this? Have I stopped sharing?
You stopped sharing, you need to reshare.
I did. Okay, so I'm gonna reshare the minute you unshare. So you guys can see that?
Yeah. Okay,
so that is, yeah, I just did that last night at about 10 p.m. and went, oh. So that, I agree with you. That is, ROC is definitely larger there. And one thing we need, and this is work that Jewel will be doing for her PhD, is she's, amongst other things, doing a whole bunch of experiments actually in high Prandtl number fluids. No one's done any high Prandtl number rotating convection, and yet core convection's probably dominantly driven by the compositional signal, which has a large Prandtl number, effective Prandtl number. So this is interesting. This is really, not yet quantitative. I said we need to go quantitative. So this is one experiment. These structures are far skinnier than the ROC prediction, but I need systematics to tell you, is there a prefactor there, right, or not? I don't actually know how it scales. I know simply a single image, and I figured it'd be cheating not to test the idea on the images I have, right? So I'm really just showing you what I've got at the moment. She is going to be doing, she's got 1 million of these really nice experiments. She's gone from Prandtl 40 to about 1,000. Mm-hmm. And this will allow us to figure out, in a compositionally driven rotating convection system, do all these scalings work? They do seem to work well so far in metal. Mm. Everything seems to be holding well in metal. I don't know yet in water, but again, that's what we'll be doing in the next couple years, is trying to make these measurements much more quantitatively, right? Much more clearly. And that's a bit of work. But I agree with you. I saw this and I wasn't thrilled. I will say one other thing though. If we're in the local Reynolds number order 1 limit, then Rossby scales approximately with Ekman to the 1/3. So near onset, it's not shocking that these should be working, right? They co-scale near onset. Now, Jewel's experiment on the right, and that's huge. That's at Rayleigh 10 to the 11, right? That's at 230 times critical. I don't consider that right at onset.
No. It's very curious.
And yet, it still, as far as we can tell from this single case, it still better fits the onset scale. So when do we truly hit turbulence? That's a fine question, right? When do we really hit the turbulence scaling? I don't know, but we're going to try to get to that. It's also interesting. That kind of maps to another thing that's interesting in these comparisons. I'm sorry if I'm heading off a bit from your question, Colm, but we pointed out that the flux-based Rayleigh number or Rossby number matches ROC squared, but only in the limit of asymptotic heat transfer, only when we hit our rapidly rotating heat transfer scaling, right? This diffusion-free scaling first put out by Julia in 2012, which you just get out of dimensional analysis, yes? And it also shows up in this scaling. It naturally comes about. And so if you look in the data, ROC squared isn't so much in the velocity data, but the heat flux-based scaling works great. Okay, that's because in the bulk, you already have the CIA triple balance, but in the actual experiments, you don't hit the diffusion-free heat transfer law numerically or in the lab because you have boundary layers you can't get around. And so when we use this Nusselt-based law shown up here, which everyone's used, it's also been so wonderful and beloved because it works, because you measure Nusselt in these experiments. And you measure Nusselt, and the bulk is roughly CIA, so it works. Yeah. But in a way, it works because the bulk is already diffusion-free, but the heat transfer isn't. So we don't exactly see, we're not going to see all this yet in the lab or numerically. Why? Because the heat transfers a huge throttle. The boundary layers are there. We can't get away from them. and that may tie into your question as well, or it's a similar comment.
Right.
When do we really hit these asymptotics?
Yeah.
And that's going to take some work to figure out.
A quick question. I can see that very nice scaling with the ROC, but you're still in the completely different regime, the very high rotating regime and the slowly rotating regime. And also velocity scale and length scales are not the same. So then any similarity in terms of flow structuring between the two regimes? You know, they are expected the same, but it's very difficult to imagine you get the same structures. You know, maybe the side might be following the same scaling.
So are you asking, are the flows similar in the slowly rotating versus rapidly rotating and
yeah, so
cases?
kind of structure following those actually ROC scaling. Do you think that they will be similar, or I guess maybe completely different?
No, I mean, I'm claiming they are innately different. I guess I'm going to go back to this slide here. Let's just play that. You know, the flows in the slowly rotating or non-rotating system are really fully three-dimensional, massively. I mean, they're all very turbulent, but fully three-dimensional with a large scale overturning as well. And in contrast, when you go to a rapidly rotating system, you're now really going, you know, you're really going from Navier-Stokes to the curl of Navier-Stokes. Now you've got a gyroscopic system, and the flows really do become very different. And you're really now worrying about thermal winds instead of just overturning free fall. And so you've really got to worry about a strongly helical, Z-vorticity dominated quasi-geostrophic flow. That's different.
Okay, thank you.
And I hope you can see that's qualitatively different. And we've tried to quantify that.
Okay, thank you. Maybe I could ask a last question. So a few years ago, John, you used to say that computational scientists couldn't access the rapidly rotating regime. You know, you used to say, here's what a computational scientist thinks is rapidly rotating, and it was going around like incredibly slowly. Would you say that they've managed to access the rapidly rotating regime at this point, or what would they need? What Ekman number would they need to get to?
Well, I think Celine has humbled me somewhat, right? I mean, if you look at what Celine has done, they've carried out experiments in 3D. Wow, that's impressive. Their 3D experiments go down to 10 to the minus 8 for Ekman. Yeah. That's rapidly rotating. That's actually starting to approach asymptotically rapidly rotating. You know, that scales into the asymptotic regime in many cases. And you can see, actually, maybe it's not yet, but it sure as hell is close. And then she's going 2D and kind of quasi 2D to get to lower Ekman numbers, to get down all the way to 10 to the minus 11. So, okay, actually, I think this is an amazing study. I'm thrilled with this. This does shut me down in any kind of snooty lab versus numerical argument. I also think that's irrelevant at the end of the day. Now, you know, if anything, we should be going the other way. Now let's start using our numerics to design our experiments, right? We can now flip the argument, and that's what we're starting to do. In my lab, we've got to model it first, as you know. Yeah. And if you don't model it first, now you're wasting your time in the lab, right? Because we can probably fairly quickly build a simple low-res numerical model and get a feel for if the lab design is sensible. So no, things have somewhat flipped on their head.
Sorry, I couldn't resist. John, hi, nice to see you.
Great to see you, Greg.
Sorry, I had my camera off, but I was eating lunch.
See, I would have liked to see that.
Quick and naive question. In your scaling of the thermal wind velocity, it seemed that you used delta T, the temperature drop across the layer, and not theta, which is much smaller in the rapidly rotating regime, whereas theta characterizes the, you know, sort of what I would call the lateral temperature gradients that are relevant for the thermal wind. Why is that?
Okay, so good point. Where did I do that? So this is key, actually, and you can thank Keith for this. I had all this wrong. and then Keith came and Keithed it. So the point is, you're right, the thermal anomalies are order local Rossby, right, which is order convective Rossby. They're very small in this system, but when we look at the thermal wind balance, it's G alpha theta, what you just said, the anomaly. But then we have a geometrical term as well. We have H over L, because the background stretching is on the large scale. It's not necessarily on H, but it's on some larger scale. Meanwhile, the buoyancy torque is on the local vortex scale. So you have H over L and you have a theta. And so what we've done is we multiplied top and bottom by delta T. And so you have theta delta T is what you said, it's small, it's ROL, but you also have H over L here. So H over L is order 1 over Rossby.
Right.
And so you actually get a cancellation between the two.
No, that's beautiful and clean. Thanks.
And again, I would point that's Keith, right?
No, I misremembered. I thought that it was
that's
G alpha delta T, the numerator of the scaling of the buoyancy torque, and I just had misremembered. Okay, thanks.
Yeah. I mean, actually, the other fun way to look at that, I must have put that somewhere. I'll never find it. Yeah, there it is. The other, you don't need to go via, you can do any of these different C, I, or A. So if you want, you could do inertial versus Archimedean. And then the scaling for this is U is square root of G alpha theta L. Well, that looks like a free fall, but it's a free fall, looks like, again, it's coming from torques, so we should be careful. But it scales as a free fall, but with what you just said, Greg, now it's theta, and now it's falling only over a distance L. So that you can see how much smaller that is. But when you put in for theta, that's ROC delta T. And when you put in for H, that's ROC, or when you put in for L, that's ROCH. And so then you get ROC of the free fall velocity, which is much smaller. So thermal wind's really freaking small in a rapidly rotating world.
Thanks, that's clear.
Awesome.
Well, thank you, John. And we're going to let you off the hook now. You've been
actually. Can I be rude? Can I put in one more pitch right at the end?
Yeah, go for it. Go on.
Thank you. You're too kind. You people are all too kind. So the one last thing I just wanted to say, I left out our lab movies, but I wanted to say that we're now building little rotating fluid dynamics kits. And if you get the chance, check out DIY-namics. We've got a Lego-based table that you can buy for US about somewhere between like $60 and $100. And it's just a Lazy Susan with a tank on it. And then you could put your phone on there, and it's a Lego motor. And if we just, here, can you guys see that? And so you can just spin your Lazy Susan and put some food coloring in. And if you spin your tank slowly, you'll get a very nice thermal wind, and you can catch it on your phone. And then you can stream your phone. And so we've created a delta T with just ice water inside our can. And so if you look on the view on that camera, it's a really nice thermal wind. And you can do this with students. You can do it for, I think, in an academic budget, right? For under $100. I think you get that for most classes. And we've got an entire website. If you look up DIY-namics, it's DIY-namics.github.io. We've got movies and parts lists, and you can do a million really good experiments here for not much. And I just want to kind of get out the word, right? This is not inaccessible science.